Hello, everyone. Welcome to this week's Smart Seminar series. We are back with another very fascinating talk, and it is my pleasure to welcome Professor Rohan Paul to our seminar series today. He's an associate professor in the Department of Computer Science Engineering at the Indian Institute of Technology, Delhi. He holds joint appointments in the Yardi School of Artificial Intelligence and the School of Information Technology. His research focuses on robotic learning, embodied AI, human robot teaming, planning, and language grounding, with a broader goal of building intelligent service robots that can interact seamlessly with humans. He has also led a lot of impactful work in assistive technologies, including innovations to improve mobility accessibility for persons with disabilities. Prior to joining IIT Delhi, he was a postdoctoral associate at the MIT Computer Science and Artificial Intelligence Laboratory. He received his PhD from University of Oxford. His doctoral research focused on models for appearance-based topological mapping, semantic mapping, and continual learning through active information acquisition. His work has appeared multiple times in multiple robotics and AI avenues, and he is the chief inventor of the SMaRT cane assistive mobility device. And with that brief introduction, please join me in welcoming Professor Rohan Paul. Thank you so much, Rohan, for joining us today, and the floor is all yours.
Yes, thank you. Thank you, Professor Souvik, and thank you, Professor Somdatta. Souvik is one of my closest collaborators. It's really, he's been mentioning about this collaboration evolving for some time. I'm really honored to be here, and Professor Somdatta as well. It's wonderful to see a community developing around this topic, thanks once again for having me here. I'm going to talk about humans and robots or embodied AI systems working together. That's going to be my theme. And in some sense, this sort of distills a couple of different research threads that I've been pursuing. And as was mentioned, I do consider myself as a bottom-up, hardware-oriented guy who started developing embedded systems, and from there on went on to learning, which eventually led to robotics, and that has been the mainstay broadly in the area of humans and machines working together. So for this talk, I essentially wanted to set the context as imagining a future where AI starts infusing into the physical world in the same way that computing has transitioned into our phones or the smartwatches, and then computing is all around. But it started from mainframes, and it started from large computers and gradually made its way everywhere, that we no longer even think that computing will not be pervasive. I mean, it's just so pervasive today. And I do strongly believe that AI is going to have that trajectory. And the physical world around us is also going to respond and become intelligent, or is likely to have some elements of intelligence. So, I think about that world, and I, want to imagine that kind of a world. And what are the technology pieces that are going to get us to a position where humans and machines are collaborating seamlessly? The specific context that I'm going to take is one of robotics, or collaborative robotic intelligence, where humans and these robots are working together either in homes or in factories or in environments which are traditionally very dangerous for humans to operate on. So, for example, security or first responder kind of applications. So if we imagine that kind of a future, we would like these machines to be able to understand what we want, and then be able to synthesize a sequence of actions in order to transform the world state, in order to satisfy what the human has said. So a couple of motivating examples here. On the left, you see a service robot, prototype from Japan, where the goal is to support the elderly in day-to-day tasks, including monitoring and fetching and so on and so forth. And one can clearly imagine a future of this kind emerging in the near future. What you see in the middle is the Bajaj factory, which is one of the auto manufacturers in India, where an engine assembly is going on, and you see these robotic arms being deployed to bring certain parts, place them collaboratively as the human is doing this complex kind of an engine assembly. And clearly, first responders and problems associated with that domain has been a very ripe ground for advancing robotics traditionally, because clearly these are areas where machines should be operating and not humans. So the question that I've been thinking about is, at an abstract level, they distill down to a certain physically grounded agent. Okay. And with this abstraction, I investigate what all is theoretically possible, going from what the human wants to what the robot can actually do in the environment. And when we think of agents, we are calling an intelligent robot as an agent that consumes a human instruction, synthesizes certain actions that go to a control system. That control system eventually leads to actuation, that the actuation is going to then interact with the environment and cause the changes, which leads to new observations and rewards. That means that you're making progress towards the goal or not, and so on and so forth. And this cycle sort of repeats. And this is a generic AI agent kind of a concept. And today, I think agentic AI is really on the rise. But there's a special case that we are considering here as systems which are directly interacting with the physical world. That means they're receiving instructions through noisy sensors. They are acting in the world through actuation, which is often noisy and error prone as well. What I've sort of augmented, which is not traditional, is this whole story about priors, because human learning is also goes through a certain curriculum. We acquire knowledge in some kind of a structured manner, and one could also imagine that the robot is also accruing observations and knowledge imparted to it directly into its decision making as well. So all of, in some sense, robotics or human-centered autonomy or autonomous systems can boil down to one equation, which is essentially we want to estimate a plan given observations, instruction, and experience. Right. So we want to basically have this function that gives me what action I should be taking, given what has been told to me to do, what I see in the environment, and what experience have I had. Did I make progress to the goal? Do I have some prior knowledge about what's really going on? Now, there are various manifestations that we can ground this story into, and the traditional paradigm that one can adopt is one of Markov decision processes, which naturally lends itself to all the uncertainty which is there in the system. And you can think of that as a variant of goal-directed Markov decision processes, and if you bring in uncertainty or partial knowledge and partially observable Markov decision processes as a way to think about these systems. We might not actually realize them in that specific way, but it gives you a good kind of an understanding towards what we are going toward into. Now, this has been a long-standing goal in robotics to develop these systems. And there's been progress in a variety of different contexts, particularly in doing short horizon tasks or repetitive kind of tasks. But it's really, today we find ourselves in a world where robots are deployed in very restrictive kind of environments, like factories is one example, or warehouses. But it's really hard to see a machine which can naturally interact in a healthcare setting or at a home, or it's interacting with students in a classroom. We don't really have those capabilities as yet. So the question, so this merits the question as to why this is so hard. Why don't we have these collaborative systems all around? And fundamentally, it boils down to one particular, insight, which is that humans are very good at having abstractions and symbolic knowledge. And we are able to manipulate the symbolic knowledge in order to think of higher level plans. We are able to, reason in a commonsensical kind of a manner, and we're very logical in our decision making. So our world is largely symbolic. We're able to abstract out the messiness of the real world, or and we are able to form this kind of a symbolic structure through which we reason in terms of theories. But the machine lives in a completely different world. The machine lives in the world of sensing, which looks like this. So this is an exact output of an RGBD camera or a LiDAR sensor, which are fairly commodity sensors that almost every autonomous system has, or a robotic platform has. And what you see here is it's a complex kind of a representation. These are point clouds. These are imperfect geometric representations. There's no semantic overlaid here as well. You can see only some part of it and not all of it. All this complexity is there. If you accumulate this, you can form these large scale kind of a maps. And this is what the machine is saying. So real problem is how to bridge this semantic gap. between symbolic structure or semantic knowledge, which we are used to dealing with as a human, and that's what really makes us fairly intelligent, versus how do you relate all of this semantic knowledge to the sensor reality of what the machine is actually saying. And that's the axis that I'm going to investigate with you and discuss with you. Uh, and various efforts in the recent past, small efforts that we've made in this direction to bridge this gap between semantics and the lower level sensor reality. So I'll transition into a couple of small research threads or small contributions we have made. And let me start out by playing a particular kind of an experiment which was conducted in our lab. So what's being shown here is an agent. So this is a ground vehicle with a robot manipulator. And what this manipulator is doing that is mounted with a visual camera, and it's scanning the environment almost like a child, and it's trying to figure out what objects are there. And the task being given is remove the debris in front. So this is a first responder motivated example. So the machine is going to pick up a block, put it on the side. It's able to reason about what is there on top, what is there below, what does it mean to be obstructing the front, and it'll execute this kind of a plan. Okay, so there is a pipe, there's a block, so it picks up the block and puts it on the side, it picks up the second one, scans, reassesses the pose, etc., etc. So it has this entire loop going on from perception to decision making to motor control, including the fineness of these behaviors of moving towards an object, then grasping it and establishing force closure, and then keeping that tight in the hand, etc., etc. Right. So this entire cycle is being sort of shown here. If you're familiar with PDDL representations in core AI, this is block world, and this is like a physical manifestation of block world that you're able to pick up things on the top, and you reach out in the inner parts of this assembly after you picked up the things on the top. So what you're seeing here is an abstract instruction, right, which gets grounded into objects. And these objects can be varied. They can be in different poses. They can be on top of each other, and the machine keeps doing that, and finally is going to clear it. Right? So this is some time ago. The machine is now been speeded up, but just want to display that the motor control is able to accommodate things like pipe and debris, and it's able to finally clear this. This is a similar example on the right hand side that I'll play. This is go to the back of the barrier and find some objects if they are on the ground. Again, it's a first responder kind of a scenario. So the machine receives the instruction, starts moving towards the barrier. It's going to execute a motion plan, and it's localizing as it goes along. And soon you'll see so soon you're going to see a certain barrier appear, and behind the barrier there are these objects. So the machine is going to go behind and then first ensure that it's actually behind. Is going to do a quick check that have I actually reached the bag, because there could have been sensor errors, so on and so forth. They're going to, like almost like a human-like way, going to check whether I'm like really at the back of the barrier. It scans the barrier, and then it's sort of ready to do any kind of a ground manipulation. This could be an object retrieval task, or object fetching task, or any kind of another assembly that could be done. So the key point here is that the machine is separated from the human. So objects behind the barrier are completely unknown, and the machine is able to autonomously reason and come up with these long running kind of plans. So it's now scanning, it will figure out what objects are there, and then report back that I see two objects there. Hey, do you want me to pick this up, or you want me to do something else with this? So as this motivating example shows what we have, some kind of an intelligence black box takes the instruction, breaks that down into small pieces, is able to reason contextually, and then respond back. So if you open the classic AI expo and start constructing this information, we progress. This is exactly how the experiment was. On the left-hand side, you see encoding of the action space. So the various kinds of picking and placing these are more skill. Some children require real life. So picking, pushing, sliding, all those kinds of things, pushing, putting things back. All on the left hand side are motor skills or control skills which have been acquired. So if the object moves around, it poses changes, there are disturbances, these skills are supposed to compensate for all of these things as lower level skills do. On the right hand side, you see the logical representation of the same action. This essentially means we're lifting these motor skills to the semantic level to say when actions are feasible and what are the effects of these actions. For example, if I pick some object, firstly, that object needs to be clear. That means I should be able to reach towards that object. It should not be blocked by another object. Now, if I'm able to reach that object, when I pick it up, the object is in my hand. That means I can't pick up another object without putting this back. And then once it's, once I'm holding that object, the space which is revealed below is now also for further interaction. So that's roughly what flavor is like. So this is like a logical description of when actions are feasible and what should happen, and that makes this kind of an experiment actually happen. So this is exactly what's been done. This task was given to a young team to make this robot actually do from first principles. And I actually did it, and that's what you're actually seeing. But the problem really with this kind of a system is a brittleness. And this has been a problem in core AI as well, that these symbolic constructs that you have, things like what is on top, what is on left, etc., if really hard for them, they become really brittle. For example, one of the funny incidents that we had in the lab was the robot was asked to go and fetch an object, like bring an object back. But what happened as it went to the object, picked it up, the object fell from the hand, but the machine did not realize. Its tactile perception was not strong enough. It thought that it's actually holding that object in front. So the machine comes back with no object in the hand and then very nicely is handing one to the human, thinking that the object has exists, till it realizes that the plan has failed and then it didn't know what to do with it. And this is very, very common with logic-based systems. If you miss one precondition, if something gets missed or incorrectly detected, the entire plan is going to fall apart. So the question is, with today's technology, can we do better? Can we now bring in machine learning in a certain way that allows us to synthesize these kinds of long-running plans, but it's not as brittle as these logic-based deterministic kind of systems. And this leads to a small piece of work that Professor Parag Singla, my esteemed colleague, and I have been doing for a couple of years, which is based on this insight that these machines have time to be trained. So if I have enough examples of an instruction that means a certain kind of a task and a breakdown of that task being demonstrated by a human, can we do better? Can the machine learn some of these concepts? That means if it is observing realizations of certain plans, can it automatically learn some kind of a representation, the neural representation essentially, about what it means to be left, what it means to be right, what it means to be a red cube or a green dice, and so on and so forth. So the problem is I have some plans being given to me. I see demonstrations of these kinds of plans. And my goal is to learn these atomic constructs of spatial constructs. Also learn things that like place something to the left, placing something on top, so on and so forth. And the key idea here is that every plan is essentially a composition of these smaller things. That means there is a neurosymbolic program of some kind, and we're calling this neurosymbolic because it's fundamentally a symbolic because it's a plan, but it has these neural underpinnings which are allowing this initial state to be transformed to the next state. And the idea here is to really think about the latent phase as having some kind of a structure. And sort of neural networks as building blocks, can we express fundamentally spatial and temporal reasoning in terms of a program? So this instruction, let's take an example. Put the block behind green dice, red cube. So that's the instruction being given. Now, if we were to go logically, we can break this down as there is going to be some move involved, okay, of some object in relation to some other object. Now that some object is predicated on being right of something, being behind of something, and there has to be a green die somewhere. So I can express all of that nested reasoning in terms of these things. And similarly, once I've identified what is to be picked up, where does it go? It goes to the right of the red cube, etc., etc. Right. So that reasoning, the entire reasoning tree of some kind comes out, and the goal here becomes: can I learn these constructs behind the if I express these as modular neural networks? Each of these is going to be a neural network that's going to take away the challenges of hard coded kind of decisions into something softer and something continuous. But the reasoning engine is going to come in and compose these modules in a certain way so that one is able to perform this particular action. So it's essentially the latent space is expressing what a human would do in terms of reasoning, and then it's giving us some kind of a way to write all of this as an optimization, something that we can optimize over and put our standard learning engine towards that. And finally, once you identified what is to be moved with respect to what, then you can actually also have an action simulator, which you can today in today's time you can think of that as a world model, which is when the action happens, then what is the transition that's going to take place. And so the model here, which comes, which eventually got developed, was something that changes the initial scene uh, through a process of visual and temporal reasoning, which is operating in the later space. So the reasoning is really operating in the land of neural networks. That means there is a latent embedding, etc., going on, and finally the action simulator is going to transform the initial data of the initial scene to the final scene. And at this point, it becomes a machine learning problem, because as you have this input, you want the output of the plan to become something, and then there's entire reasoning, and then you can back propagate to it. Now the challenges are that there are going to be some things that are neural, but the things that are not neural, we play the technique from reinforcement learning, which is the reinforced rule, that allows these non-differentiable parts to be handled in a slightly different way, where one is able to optimize and do that. So with this machinery, we get the ability to look at different plans, view them as instance-specific reasoning chains grounded on these neural constructs, and acquire these neural constructs operating on the state space and the action space, resulting in autonomous reasoning of this kind. So let's first see something on the left-hand side. So the instruction being given is, put the white dice above the yellow Lego block and move the yellow cube to the top of the white dice. So it's a slightly, let's say, unnatural instruction, but it really, sheds light on the kind of reasoning that needs to happen. White dice above the yellow Lego object and move something to the something kind of thing. So on the right-hand side, you see the rollout of this plan being executed completely. This autonomous run in a simulation engine, where you see the plan being conducted. So you saw, one block being put, and then the second block is being put. This is correct. This is a two-step kind of a plan. Now, what if we were purely neural? What if we take the complete, the simplistic machine learning approach to say, I have this input data, just transform and, do all your reasoning in one giant system? It can't happen. And it doesn't happen because it starts being okay. So it does the first thing sort of okay, but then it gets really confused as to what is going to happen after that. And the plan essentially, fails. It'll do the first thing correctly, but then get confused, and then it'll stop. It can't go further. And it's able to, and this is happening because neural, it takes a lot of effort for neural models, though theoretically they can acquire any kind of a reasoning chain. It's really hard with limited data to be able to see that. So that's why you see shallow reasoning on the left hand side. And for the kind of reasoning that we're interested in, long running plans, complex kind of a reasoning, the path forward is neurosymbolic, which expresses explicitly these plans, and that's allowing this progress to sort of happen. And we can take this, run this on steroids. So on the left-hand side, you see a monologue. Put this thing to the right of something, then play something, then play something, and play something. So this is a fairly extensive kind of instruction being done, which is being accurately executed by the robot. It's doing all of that assembly. It's almost like, I can say that I have all of these Lego blocks, make that entire Lego for me. It's almost of that kind, which is being shown here. The machine is able to do that. So this is an accurate rollout one after the other. All the predictions are correct in this case, and the plan is actually correct. One of the byproducts of having these modules is the ability to see reasoning step by step, which in today's world, you can think of that as something like chain of thought, or, explain to me step by step kind of a thing. And the technology does exist today to even render these scenes in the middle. That means for all of this entire big plan, I can make predictions as to how the scene is going to look like if I take the first action, the second action, the third action, so on and so forth. And this is happening because neural models are able to go between, let's say, visual representations and an entire image itself. This work predates today's generative models like diffusion and others, and this is a simplistic architecture. But even at that time, this a couple of years ago, one was able to look at the plan as to what is going to happen in the world state and render these images. So even before the machine has started building this construction, we're able to visualize what the scene is going to look like step by step. And this is really useful. This is really useful because you can roll this up in a model predictive control kind of a algorithm, which will also detect if plans fail. So we had a follow-on work on this, which essentially used these predictions to say that, well, the robot would make an error, or we would detect an error if my visualized or imagined scene does not match with what I am seeing to a certain degree. Right. So we could then trigger our error recovery. We could do a replan. We could see how much progress has been done, what part of the plan can be preserved, and then execute and complete that kind of a plan. And this is made possible by the modular architecture. If you had this monolithic thing, then it would not be able to say much, or it would be harder to say, at least, it will be harder. But with these modules, one is able to visualize these long-running plans and then being able to recover, these plans as we go along doing so. Right. So what did we accomplish? So essentially, this is about learning these primitive constructs, left, right, and others. And one can think of that as robot kindergarten. So, you learn things like left and, basic primitives very early in school. So something of that kind that, the robot has done some kind of homework and it has these primitives. And then during exams, is able to put these things together and execute these kinds of instructions, which were never seen during training because it has this ability to compose these modular structures. Okay, so this was about pick and place, right? Pick something up, place something there, and this is really useful. This helps in debris clearance. It helps in, let's say, service robot. You can ask it to bring and so on and so forth. These kinds of tasks it can do. But what about things which are complex from a dynamics viewpoint? And this is a wonderful collaboration with Professor Souvik that we've been engaged with more close to 3 to 4 years kind of a time frame, which looked at this whole thing about pick and place being standard in robotics in some sense, right? So robots are always doing picking and placing a majority of the time. But what about the ability to deal with dynamics? That means, can we deal with things like collisions? Can we deal with sliding? Can we deal with projectile motions, etc.? And can we reason over these things? And one of the motivating, so we had this motivation from two different directions because Professor Souvik is an expert in physics informed learning, and we were discussing, and he was talking about physics and how physics can come into neural networks. And our motivation was something of this kind. So this is a firefighting robot, which has been asked to, put water into a certain, kind of a window where, let's say, there's fire coming out, and you want to put something from there. Now, this is a dynamic thing. This is not pick and place. You have to reason about gravity, projectile motion, parabolic, etc., etc. And this is not easy. This is a little bit complex. And you can do more interesting things. Let's say you want to take a rebound from somewhere else. Okay, so let's say there's a lateral wall and you want to take a rebound, then you have to reason multi-steps, not just a single step kind of a thing. And around the same time, there was work from Kelsey Allen at MIT at that time, who actually showed that physical reasoning about sequential physical tasks is actually challenging for AI systems. So on the right-hand side, there is this game that they developed from a cognitive science kind of an investigation, where one needs to figure out how exactly to get this ball, into that green vessel. And it has to be dropped at the right height, at the right location, so that it has enough, momentum so that it falls, right? And they actually showed that DQN, or the state-of-the-art reinforcement learning model, really, really struggled because of the continuous dynamics, fairly sensitive rewards. Like you slightly change your angle at which the ball is falling or the height at which it's falling, it has a drastic impact in the subsequent plan. And one step is hard, multiple steps is harder. It's like really hard to get these plans to work. So Souvik and myself started looking at this problem. from a robotics point of view, and essentially came up with the following kind of an idea. Firstly, we realized, and in fact, not us, but our students realized that even simulating dynamical interactions is hard. It is really, really slow. So if you were to show this kind of a machine, let's say there's a ball, you want to get the ball to a particular destination, and hence you would use a pendulum to hit the ball, then it'll slide and then fall. This is really, really slow to simulate. If you're doing a physics kind of a, running a physics engine like, Isaac or NVIDIA Isaac ecosystem, it's like really, really slow to do that. So no matter what we did at the planning layer, we were going to be struggling because whatever we do, we would have to rely on simulation, and that's what really not panning out for our students at that time. And that's where Sauvik's expertise came in. He has mechanisms, or he has this theory of how do you observe certain trajectories and learn essentially a physics grounded world model. So let's say you observe from a high fidelity physics engine what swinging looks like, what sliding looks like, what throwing looks like, what collision looks like. And can we use these rollouts to actually learn a world model, or let's say a goal condition or a task condition world model of some kind? So the idea is to have a, essentially a trajectory predictor, which can even visualize, but regularize it with, with physics, and the differentiability, etc., comes in. And what is not modeled in physics goes into the data part. And then there's a nice, beautiful theory that allows these networks to be learned. So we're calling that skill networks as something that predicts these dynamics. And this gives us a lot of power. Firstly, that they can deal with coarse physics. That means if you understand something about the physical process, that's enough to have some gains. The second is really, really fast by an order of magnitude. And if we combine this ability to visualize the effects of actions, we are in business, because then we can start planning. So the same problem of getting the ball to a distant kind of container through a sequence of hitting and sliding, so on and so forth, now becomes essentially a forward state space planning problem with continuous dynamics being imagined essentially through this physics simulation. So you see, this is essentially model-based RL. So MCTS is the line of attack here, or Monte Carlo tree search, which is doing this there's a forward planning, where you have this initial state. You visualize what actions can I take? Can I throw at this height? Can I throw at a bigger height or a lower height? And then what happens comes at the second one, and then the third one, so on and so forth. And you can run these kinds of physics simulators inside this planning loop and say where you're going to make some progress. And this allows exploration. Now, this makes RL really feasible, and one is able to actually show this in practice in a simulation environment. So on the right hand side, you see there are two robots. So these are static manipulators, which are going to build this simple machine for us. So they're given this task of getting the ball. There's a slide puck here. The puck has to go to this location. So it figures out that one of them is going to make this pendulum. This pendulum is going to be dropped. It's going to hit the puck. And finally, this has to go to this point. It can't go no matter what you do. So you have to have a bridge of some kind. So this bridge has to be brought in, and then it's going to fall here. But it doesn't come directly. So what you're seeing here is one of the earlier rollouts, right, where there's a failure. The machine figures out that this was too far away. This has to be brought in here. And then gradually through trials, this is really model-based reinforcement learning happening on the fly, right? It's able to then, it'll figure out that the correct angle or the line in which this needs to be kept. And then when the puck is then slid, then it's going to go over this bridge and then fall directly into the container, which I think is going to happen now. So it's figuring this out, right? So this is essentially this kind of a thinking going on, and you see success, etc., etc. I think over time it'll happen. So I think the final rollout is somewhere here, etc., and the ball actually falls into the thing. There's a subtlety here. There was essentially a Gaussian process also running, which was finally compensating for the imperfection in physics, and so that GP was also being learned on the fly, right? just to show this a little bit, so the previous one was the archive version of the paper. Eventually, it got refined and appeared in AAAI this year. This is sort of showing this entire piece working with some other bells and whistles. So this is the planning tree being grown, and the machine is thinking about various options of building this machine, and it's doing these trials in the mind, and then it'll finally figure out how to solve this particular task. There's an additional piece that, again, Professor Sauvik is very instrumental in getting into the system, was this GFlowNet-based reasoning over the tools themselves. So essentially, it's not just about sequencing these tools, but it's also about which tools are going to be needed. They can be different coefficients of frictions, coefficient of restitutions, and we need some engine which is also reasoning at the semantic level about these things. And GFlowNets have this beautiful property that essentially you are able to sample for exploration. You're able to sample with respect to reward, not just goal reaching, but you're able to sample diversity in reward. So here you want the distribution should be not delta functions, but really spread out in terms of entropy, and which gives a lot of options to what these machines could be. Could you have one or two of these tools? You need more tools, etc., etc. And this really plays a role. So this is the entire engine running on top of Monte Carlo tree search, which finally sort of solves this problem and gives us a way. So these are the successful rollouts. There are the same tasks that Kelsey earlier had talked about. They were lifted into the embodied domain with robotic simulators, and you see all of these machines being constructed. On the right hand side is a bridge task that we described. This was being operational here, and this is the wedge. So you change the wedge, it hits in a particular way, and one is able to solve the task. And the key message here, and may sort of pause here, is the fact that physics really helps. Right? Without physics, this is a hopeless kind of a problem. Continuous domains, long horizons, sparse sensitive rewards. There's not much hope for exploration to do much. If you bring physics in, one is able to sample in a much more physically consistent space, etc., etc. And this work would not have been possible if there were no physics simulators that we were able to really leverage. And just to draw your attention to what from view, this is field plan system in terms of reasoning time and in terms of regret. And the reasoning time is fairly low compared to any other model-based reinforcement learning. This is the MVPO, which was a slightly generalized version of continuous space Markov tree search for reinforcement learning. And the reasoning time is really large. Even the model-based approach on reinforcement learning was not able to show effective results. And this provides a fast kind of a mechanism to find these kinds of solutions which are there. And again, more can be done. There's an extension that our team is looking at in terms of recovering physics as well, right? What if we don't have the exact equation? Can we recover parts of it? And that's the line of attack at the moment here. So what this work really enables is robots that can deal with continuous interaction. Let's say we were thinking about another case in which a ball sort of comes and falls in front of the robot. Can the robot even figure out where to move so that it doesn't hurt itself? Right, and that again would require these kinds of dynamic reasoning, etc., and something that still requires a lot of effort, more effort to be put in order to be useful for future. Okay, I've talked about interactions, pick and place. I've talked about dynamics. What's also very central to our story are objects, right? There is fair amount of evidence from cognition that objects are fairly central to our reasoning. This has been a view, particularly from cognitive science, which has observed that children acquire the ability to reason about objects in terms of permanence, in terms of occlusion, etc., fairly early. And we always talk about objects, right? Pick up this object, throw this object, do something with this kinds of objects, right? So object models are really, really, fundamental in autonomy. And we are considering cases, let's say in the care setting or in the first responder kind of a setting, where we might be operating in an environment with maybe an open set kind of an object distribution, right? So we're not in a constrained kind of a setting that, okay, there are only 5 objects that we are going to be interacting with. There could be newer objects. They could be, very diverse looking kind of an object, which goes beyond a training set kind of a distribution. It's not a fixed set of classes that we consider here. So how do we deal with this, right? How do we figure out or do something about objects, as if I bring an object, put it in front of you, and ask you to build a model on the fly? So this is something we've been investigating. This is work with Dr. Sheshtuli, who's a former student actually, and who's been working with us largely on object-centric planning and task planning. And within this was a collaboration on how do you actively acquire a model of objects. So the idea here is to leverage, or in some sense, make objects really squishy as a neural network. So we can represent objects. Let's say there is an object of this kind, right? So we can represent this in terms of point clouds or meshes or voxels. That's a standard representation. But what if we can, make this continuous in terms of, let's say, a field? That means it's a spatial field where I can take any point and tell you what is its opacity in terms of materialness and what is its appearance. And I can change for any other objects. If I take another object and let us say this is where the material is, anything inside of that, and anything inside this level set becomes something where there is too much material, or this is the interior of the object, and everything outside this level set becomes available for us to do any kind of free-form interaction. Now, in this kind of setting, what we are really looking at is a neural network, okay, which is able to predict which part of the space is occupied and what's its appearance, and which part is unoccupied, and we can do anything we want to in that particular area. And this representation essentially become very popular in graphics community or vision community, called the NUF representation, which has also become Gaussian splatting today. And these neural representations of objects and appearance is what gives us a path forward towards doing something in a fairly incremental and a general kind of a way. So the idea is that the robot wakes up, there's an object in front, and it starts acquiring observations in certain information gathering kind of a sense. So let's say it takes a certain view, it learns something about the object in terms of these are the frontal faces, these are right faces, right face, the top face, etc., etc. And then maybe it does not have knowledge about the rear part of the object or behind what is the material density, etc., because it's not seen that. Now, could we somehow quantify that in an uncertainty with an uncertainty metric and say that can you move your hand to the maximally, to a location which can maximally reduce uncertainty, which is actually information gain. So move to places where you will gather more information, and hopefully that process will end at some point of time, and then you should have a model of the object. So that's the kind of system which was developed. So you're seeing here on the left-hand side, initially it's a very uninformed kind of an object. It's very hazy and one doesn't really know where the faces are. And gradually you see the clearing up of the myth, figuratively, that you get an observation, edges get refined, they get refined further, you actually get a fairly nice cheesed box for you to start manipulating, and then the manipulation can actually happen. So the idea is how do you go from here to here with this kind of a representation, and that's where this whole story came in. That the NERF model is essentially a neural network. And what we can bring to bear to this problem is uncertainty quantification, which was ensembling in our case. So let's say you jitter in a Bayesian neural network setting, you jitter the model parameter, and then you see the variance happening in its predictions. And where is the variance actually? So it's essentially model dissonance. And if we can quantify that model dissonance, it gives a measure of uncertainty. And then we can go to uncertain regions and acquire more information and put things there. To somebody who comes from cyber-physical background, this is very similar to sensor placement. So if you have n sensors in a location, you want to measure in information, in an informative kind of, let's say water quality monitoring, seismic monitoring. These problems are very similar. They have this kind of a submodular structure. And this is something that we're leveraging in the 3D space to acquire this model. The additional bit here, information gathering for was sort of known, but what was not known or what was not done before, the fact that we have an object and the object may need to be interacted with during the process of model construction. So say the bottom of the object is on a table, right? We know nothing about it, but if you go to grasp that and look at it by tilting it, and that's model here. For so it's a chicken kind of in terms of how do you grasp objects, wherever you are to adjust the be grasping from the uncertain region. So you have to maximize your grasp and figure out how to pick up from the region you're and to certain which is feasible in and gradually your grasp quality also improves. So the information goes into the grasping itself, and that's why it becomes a fairly interesting grasp, tactile exploration kind of a problem which is being displayed here. That not go for the nearest graph, you don't go for the nearest graph, you go for the graphs that you're most certain about the outcomes, more certain about stability, and only then you're able to do that. Otherwise, it's going to fall behind. That's what's being shown on the left-hand side. And you need that information, uncertainty, getting it motor control in order to make this. So let's see the action in terms of a simulation. Here, this is the this is trying to make model. So this is 0. You see this cloud, and the cloud then going to be chiseled out with the observations, etc., etc. And you gradually see the PSNR is improving. That means we get a better model as observations are required. And you see on the left-hand side that so the views and then they'll change wherever there's more uncertainty, and gradually the model is going to make its way. So the PSNR keeps improving. Things happen. Collaborative. The besides the point is that the robot was a bit less, so we could not see from the other side, and as has been done. But it essentially shows this kind of an active kind of a way of acquiring this. The way it's set up is an active kind of a setting. That means the robot is not in supervision on how to explore; it's doing this on its own, and this is sort of important in robotics because a lot of times the robots are sitting. They are they're given time to execute that, and this. Right. The question is, what should we be doing in the next time? And this is like saying, well, at night, what should a robot do? Right? In the morning task, what it should be doing? Maybe it should be doing understanding objects it did not understand very well. Right? It picks up, I saw this object, I was, I had 3 failed graphs. Why did I fail? What are its physical properties? Can I learn something about it? Right? Do that homework for the next day, and the next machine becomes better. And this will essentially give us a path forward to lifelong learning of these agents. We're able to refine that because no matter what we do, also kind of setting new objects are going to come in. Old objects are going to change their affordances. They're going to break their, physics is going to change over time as well. And this adaptation is going to only happen when learning in a self-directed kind of way. Something like children do naturally, right? Really curious when they cannot will go and collect target data. And in some sense, this is much more needs to be done. Today, this is being thought of as real world RL, and it has that kind of a thing, right? Curiosity driven without a can you set your own goal for the purpose of constructing a better? That's an exciting idea. Something as action, we are physically embodied. And it provides a very rich avenue theory to be developed moving forward. I'm going to start winding up soon and to mention other aspects. We complete this from objects to dynamics, etc. And the question I'm not mentioned here is about the motor behavior themselves, or the skills themselves. And skills are really, really important because somebody has to picking, placing, pushing, etc. Right? And it's really challenging to get these skills to work in a robust way. And increasingly, the progress which is being made in imitation learning is coming in handy. So what do you, so this is about 2 years ago, where the machine actually, the machine had arrived, and we were looking at what we can do with that arm and testing. This is called the yellow system. This is Berkeley, which we have reproduced in our lab and adapted now. And here is one of our another who are trying to basically operate a pushing kind of a task. You want to push some object away, right? So this was being done because pushing is not easy. Pushing is like actually very, very difficult, particularly when you don't know the physics. It leads to a lot of, arm breakage and, physics not going in the right kind of a way. Stable pushing actually very hard. That's why we started doing that. But today, with advances in imitation learning, this kind of technology is coming. What if I demonstrate through kinesthetic teaching these kinds of motor skills? Can I acquire them, for the long run, right? So instead of programming, which is where I started with in the initial experiment, by saying, okay, here, then do something, demonstrate to a machine by a human, and the machine. And
Rohan,
you see,
Rohan, can you hear
yeah,
me? Your
yes,
voice
yes,
is
I can.
constantly breaking. Is there a way that you could change the internet to some other connection?
Is that the case? Let
Yeah,
me.
For
I
last,
mean,
yeah,
Has that deteriorated in the last few minutes? Is it?
yeah, for
yeah,
the
last
last like
last
10 minutes.
1 2 minutes,
It's
not
10
10
minutes.
minutes, 1 2
Something has
minutes.
happened. Maybe. Okay, let me just, if it's okay, I can just try and find another location. Let's try this one. Is this slightly better?
It is better. Yeah.
It's better. Okay, let's try this. I apologize. All right. So about skills, right? And the fact that if the machine has been shown these kinds of tasks to be done, can it do these tasks on its own? So here you're seeing some kind of a packing task in terms of objects being picked up and being put inside a basket, and just see the motion that this machine is generating. And you sort of notice that it has a human-like kind of an ability. So just see this part, let's say, and just see how it is going to bend, right? And these kinds of motions. These are very difficult to program. This is really difficult for a model-based system to arrive at. With some effort, maybe it can. But this is something that the human does naturally. The question is, can we acquire these things directly from demonstration? And there's been a recent explosion with a number of very significant development in terms of architectures that have come up, largely inspired by large language models or the efforts in vision language action kind of models, etc. On one hand, and on diffusion on the other side, has been very active. And something that a group has been exploring is, can you do long horizon tasks with this? Can you do an entire assembly kind of a task or a packing task with this? And the idea here is to not think of the entire task as one big task, which is this theme that I've had throughout this presentation, is to break things down into modular things. And can we do that also now in the control space or in the action kind of a space? And the idea is that, can you actually have these sub goals being discovered, being extracted from this long demonstration, and something like what a teacher would do in a school, that you have this complex problem, let's break this down, and then you do the smaller parts. Essentially, this kind of sub goals provide anchors or intermediate anchors for this kind of imitation to progress in a fairly nice kind of a manner. And what one can do here is, this is essentially imitation learning, that you're looking at expert demonstrations and trying to reproduce these motor actions by the expert. And through a transformer kind of an architecture, you can bring in the notion of sub goals again into this, so that it sort of naturally goes through these one sub goal at a time, not this entire demonstration, and is able to accomplish that task in a sort of a stage-wise kind of a manner. So let's see this motion again. So you will see a long horizon kind of a demonstration. Let's say you had to discard one box, you have to pick up another item, put it back in the basket, then close the basket itself, etc. Now this has been essentially learned as subtasks. It is extracted out the subtasks, learn these little control routines, and then is piecing that together on the fly, which is very similar to how we started in the first place. We had these simpler neural modules. Now they have become policies. So these sub policies or skills are being discovered by this architecture. And what you're really doing is attending over these sub goals as you go along. That means that, okay, what is the first thing that I can do? What is the second thing? and then it'll actually do that. Of course, it's not perfect. You'll see some incorrect examples here where it sort of messes it up because it's not done that kind of an exploration. So it is going to miss, it just missed a particular object. There are limits to imitation. I mean, it does work to a certain extent, and it has increasingly been very, very successful. But there's still scope for reinforcement learning because it's not done exploration and it finds something bad and then it becomes more and more bad. And that's a very that's catastrophic forgetting, which is very typical in imitation learning to happen. Okay, so this is about skilling of robots from human demonstration. And it's sort of important kind of a development in the field because it opens up, I would say, another employment kind of an opportunity, just as data labeling was there for ImageNet kind of applications. In today's robot autonomy, maybe human demonstrators are going to be employed to demonstrate these skills and train in certain kind of a way. But let's explore something else. Let's explore humans being skilled through, robotic systems or embodied systems. And then it goes back to, the work that was mentioned initially in the case of assistive technology. So we'll slightly go away from robotics, but carry forward some of the same ideas. I've been looking at this problem of mobility, not for autonomous robots, but also for persons with low vision and with blindness, motivated by the fact that in India, we have one of the largest populations, blind populations, and they are really restricted in terms of their mobility because of not being able to negotiate unstructured environments. So here you see the white cane, which is a traditional tool carried by visually challenged persons throughout the world. And this white cane cannot detect anything from knee to head height. Right, it misses it completely, and then you would get upper body or face kind of injuries. And the idea here is something really simple, that you augment this with sensor technology. That means you have some kind of a ranging, this ultrasonic ranging. It can be anything else as well, that provides this pre-warning in terms of an accessible interface through vibrations or through acoustics, typically vibrations, because acoustic localization is required for other kind of a safety thing. So this is now fairly commonplace in the sense that sensor canes are available in India, and not just what we developed, but even other efforts are there, and variants of this have emerged. And today this deployment stands at around 2 lakh units are in the field. So this is one of the users, a couple of users in different parts of India using this technology. This is transition to the industry, and industry has taken this forward in terms of an actual product, which is distributed under the Government of India's APEX scheme for assistive technology. So this is in Bangalore, where you see a person using this to avoid, an open window in a corridor, et cetera. And here you see another person avoid vehicles and navigate safely. These are trial at the National Association for the Blind. And one is able to negotiate. There's something happening with the video. But you get the point that essentially one is able to use this directed sensing to find a clear region. So it's like a go, no go kind of a classification, and then being able to do that. But the problem with this kind of a technology is that this requires a certain amount of training. It requires one to be able to direct sensing in the navigation path and tap in the right way. And this has become a real problem in scaling nationally. It's part of the national program, but training is one of the critical limitations in this, because how do you tell a person to point this entire unit in the correct kind of a way? So we've been sort of thinking about this in the modern context. So after more than 10 years of this technology being in the field, can you actually have a different way where the device itself teaches you how to use me, or how should the person use the device itself? So the idea is to use inertial sensing to in the real time figure out what exactly is the angular movement in the sagittal and in the lateral, in the middle and the sagittal planes. So what is the angle with respect to the ground, in terms of the vertical plane, and what is the sideways kind of a tapping going on? And can you get cues in terms of, is this nominal? Is this, abnormal, or is this something to watch out for, right? And the idea here is to have a neural network that looks at this high frequency data from the IMU, runs on an embedded platforms. That means it has to be really, low power and low compute, and it has to be fast, and the effort which has gone into this kind of a thing. And what it does, instead of giving, apart from having no-go kind of an information, this acoustically tells you, are you in the right way or how should you turn? So it'll sort of say, some kind of a sound will be produced so that the person sort of adjusts on their own what is nominal holding angle. And then you can monitor it remotely. So this is, over the internet, in the sense that a remote trainer can get access to this information. And then finally, you get information, are you doing this right or is this sort of wrong? So it becomes like a learning tool and it's being evaluated where mobility training happens. And that's in some sense the idea. So it's sort of the other part of the story, that humans are skilling machines, but machines may also help, skilling to happen for a person. Right. So with that, I would end by, the couple, 2 or 3 takeaways from this talk. One is the embodied AI is an emerging future. It's something exciting, particularly if particularly since the ratio of autonomy or utility per unit cost, being a metric which is improving with low cost sensing, low cost compute, but also what we can do in terms of complex tasks. And that's what makes embodied AI, something interesting for today. And to be useful, we've got to go beyond simplistic tasks. Like pick, place, look is what drones do, and that's been the mainstay for this line of work. We've got to move beyond complex human-like tasks to be useful in human-centric setting, and that poses challenges for both academia and also industry. But academia really needs to figure out what is the theory that will get us there. And the one message that I would have from today's talk are physically grounded modular abstractions, both in the spatial space and in the action of the temporal space, are going to have, at least they provide a path forward towards generalized complex kind of a reasoning. We saw that in terms of modular spatial reasoning, in terms of dynamics, in terms of imitation learning. This is all about breaking a bigger problem down to modular abstractions that can be put together to perform a more complex task. And finally, because we have actions, the robot can interact, we've got to think about lifelong learning and distribution shifts and compensating for distribution shifts in a fairly interesting way. And there's avenue to do more interesting work here, that the robot itself figures out what practice it needs to do to get better over time. And that's going to be something really fascinating in the times to come. And with this, thanks so much. I appreciate all of you coming here. I profusely thank all of my team. It takes a village to do this kind of research. The student staff members and esteemed colleagues like Souvik and others, and Parag Singla and others who've been working with me. And with that, thanks so much, and really appreciate. And if you have questions, I'll be happy to answer.
Thanks a lot, Rohan. So we have questions. So Rakesh, please go ahead, ask your question.
Thank you so much for an insightful talk. I have 2, 3 questions. So first of all, how to plan the next step, like for the end effector? What kind of model you are using to reach from one step to one location to another location? So this is my first question. And should I ask all the question at once or?
Sure, you can ask.
Okay, so the second question is how the robots hold any substance. So is it generalized like that chicken and egg problem? So because there is a problem of good models, and because if the material is soft, it needs to apply different forces. The material is hard, it needs to apply different forces. So how it holds any substance, how it learns that if any new substance come, a new object comes with a different density of material or different type of materials, and how it will hold it. And the third question is how point cloud represents unique shape as because point clouds are not one-to-one mapping, because for a different objects it can generates the same point clouds. So how it differentiates that this object is different from this object?
Sure. So let me answer that, right? Maybe I can go in reverse, right? So I think point clouds is essentially not just the, I mean, it is both geometry and appearance. Okay. So, objects are, even if they have the same geometry, they may have different appearances, right? So this representation is capturing both. Secondly, a lot of things are going on under the hood when you're fusing point clouds from various different viewpoints, etc. So you're able to see the object in its entirety so that you can later manipulate them and so on and so forth, right? So there's an entire pipeline which is there, which fuses both the visual information and the geometric information so that you get an accurate object model. So that capability is there. And to get back to your earlier question about how is it actually moving, so it moves in two ways, right? So we move by either planning or by control. So by planning, you mean that we figure out exactly, if I have to pick something up, I'm going to extend my hand, go above the object, descend down, and then gradually make contact with that object, right? So I inject those kinds of subgoals that go here, go there, etc., and then they become shortest paths. And then each of these small waypoints are controlled by controllers. So motors get actuated, they'll go to the next position, then the next position, and the next position. And gradually the hope is that one is able to get to that final destination, right? So it's a combination of control and planning. And third part was about adaptation, right? So that's a nice part, right? So part of it gets handled at the control level, part of it gets handled at the planning level. Let's say that if we have tactile sensors, or at least we have some information about force that is being exerted, and one can monitor that and figure out whether we made contact with that object or not. And if it sort of deforms a little, then we can apply force till we get a certain kind of a force feedback. That means we have a stable kind of a grasp. Now that is what the controller would do, which is low level reasoning. You can also do higher level reasoning, which is the kind of stuff that I talked about before, where you can also start inferring the latent parameters of the friction, or the latent parameters of what the object is actually doing, and reason over that as well, right? So we have that ability. It'll do that information gathering. It'll make a belief and deal in a probabilistic kind of a way. So if you're familiar with Bayesian inference, it is something like that. These parameters are latent, and you want to get observations so that you can refine the model and get back, you can revert to that object representation. Yeah.
Thank you. But can I ask a follow-on question, like for
You should
Just
ask me
one.
Yeah.
Just one.
okay, okay. So for the planning of the next step of the end effector, actually I was asking for the action space, like how it controls, means control using controls, and like if it goes from one place to another place, there will be acceleration. So the jerk will be there. So if it is not a continuous path, and how it smoothen out, take the smooth path
Yeah.
or
So
optimal
so
trajectory.
yeah. So it's a theory, right? So there is a motion profile that gets generated. So basically, it becomes, you can think of that as a differential equation of some kind, like a time varying thing. And a motion profiles, there's a theory behind that. How do you generate motion profiles? So think of driving a car, or doing going on a cycle, right? So you modulate your velocity, etc., based on the terrain. And if you want to stop, you don't stop immediately, typically, until there's an emergency. If you see a friend, then you will decelerate and do that. And robots do the same thing, right? So you basically can have a motion profile where velocities increase, then they go down, and you modulate accelerations. And if you're worried about jerk, then you can go into the second, you can generate minimum jerk trajectories. You can reason at a certain higher rate, and then you can fuse and get trajectory. So it's called trajectory optimization. There's an entire field of these kinds of techniques, which is figuring out control, which is regularized, which is smooth, etc., etc. Right. So some of these things we take up in teaching. So maybe at that time we can discuss some of these things.
Okay, thank you so much for the insightful talk again.
Any other question? We might have time for only one. So, okay, Divakar, please go ahead.
Oh yeah, thank you so much. I will not take a long time. Thank you so much, Professor Paul, for this wonderful talk. I just have a quick question regarding the work on pipeline. And could you please help me understand why the model-based PPO have was doing worse than the model-free methods? Because I would expect the model-based methods to work better than the other methods. Yeah, could you please highlight that?
Okay. So, so when you say model free, right? So model free are going to struggle because of the continuous space um, and the sensitive reward things, right? Because model free does not really understand that there is continuity, and those kinds of things are completely absent. So they are going to struggle because the exploration space is too large. right? So that all that family of techniques which are not doing that, they just find the space to be too large to do anything reasonable. And maybe if you run it for a very, very long time, maybe they'll find a solution somewhere and then lock onto that. But that's typically not something that typically happens. They really struggle. Now, when you look at model-based kind of an approaches, right? Um, there are two kinds of model-based approaches. One is the kind of approach that we have taken, which is more structured, which is more semantics, and it is grounded in the task that we are trying to perform. So as you can see, sort of see that we reason about the tool which is being used, and then the interaction with the tool, and what interaction is going to happen, and how this is going to fall through. So there's some semantics that we are leveraging. Now, what if you don't leverage the semantics, right? Let's say you treat these as simply any kinds of balls or Lego blocks that you can interact with, or you can throw, or you can have collision with, and so on and so forth, right? If you treat it that way, then it becomes uh, the other technology that we talked about, MBPO and those kinds of techniques, which will learn dynamics in a certain generalized kind of a way. They don't know that these are rigid objects, or they're doing in that kind of a way, right? So our approach works better than model based, which works better than model free. That's where roughly the things line up. And the fact that we have really physics grounded things and we explore in a certain way is the advantage, and that's why it's able to do the thing, solve these tasks, right? Okay,
Yeah, yeah. Thank you so much.
thanks.
Thanks. So Rohan, I have one question. It's a very beautiful
Yes.
presentation, and got to see this overview. I've never seen this overview. So thanks for actually giving us this great overview.
Yeah, it's
Just one.
I am only a part of the story, right? So it's all the students and my collaborators and the team.
That I
It
appreciate. Yeah.
takes a team to
So
do that.
when you were showing this, I believe it was called neurosymbolic thing, which you did with Professor Parag. So there you mentioned that that without the neurosymbolic thing, the simple neural network got confused over placing the white, I believe the white block over the yellow block, and then again a yellow block. So was it because it confused the yellow block that it had to move on the top of white block with the one that is already placed underneath?
It's actually one never knows, right? So
Oh,
this is a black box prediction that comes out, so it's very hard to say why it got confused. But essentially, it is the fact that it sort of memorized something from before, right? And when you give it a new instruction, it's not able to see that there is going to be this kind of a change. So it's
I
taking the
see.
new instruction back to whatever it has seen. And maybe at that time it has seen what you just said. Maybe it's seen an example of that kind. It's trying to map it back to that particular
I
thing.
see.
And it's really shallow. So the errors keep compounding further and further. That's the problem in completely neural. That little bit, chalo thoda sa kar liya, like little bit it'll try to do, and then it gets confused after that. Then it's not able to figure out that there's going to be this drastic change which is going to happen,
I
because
see.
it's expecting data in those kinds of regimes, and it becomes harder and harder to do that. Yeah.
Great. Thanks a lot. Thanks a lot. Brilliant presentation. Thanks
Thanks
a
a
lot
lot.
for joining in.
Thanks,
Um,
Rajdeep. I really appreciate, as I
thank
mentioned,
you.
right? I've heard of this, from before, and really honored to be here. Thanks so much. Thanks for your time.
Thank you.
Thank you.
So we'll again join next Wednesday around this time. So until then, goodbye, everyone.
Thank you.
Bye. Thanks.